Right, so in this video we're going to carry on with the Feynman Diagrams concept. The idea mostly is because we need to look at another form of interaction, and that is what mediates nuclear reactions. So far we covered the photon as a mediator of electrostatics. And then there's two other fundamental forces that we need to be aware of as well. We need to be aware of the weak nuclear force and the strong nuclear force. Now, the strong nuclear force and the weak nuclear force you've come across before, whether you realize it or not. Now, the weak nuclear force is mediated by what we call W bosons, okay? And now you can actually have W plus, W minus, or even actually W zeros, which mediate the weak nuclear force. So the weak nuclear force. So what is the weak nuclear force and where does it occur? Well, it occurs with, very specifically, beta decay, which hopefully you're going, oh yes, I remember beta decay. I remember that now very clearly. Excellent, no problems. And we will obviously have reviewed beta decay when we looked at the subatomic particles in lesson, because obviously beta decay requires the antineutrino and neutrinos in order to balance lepton number. If that makes no sense to you, then you obviously want to go back and watch the particles videos on my channel. Right, so first of all, well, we need to cover one more, don't we, first? There's one more which I mentioned, which is the strong nuclear force. Now, the strong nuclear force is governed by gluons. So these are W bosons. They can also be used by Z bosons as well. I meant to say that, Z bosons. Z and W plus, minus, and zero bosons. And, but gluons, written gluon, I suppose I should write these are bosons. Okay. Now, gluons are what are responsible for the strong nuclear force. So the strong nuclear. So the strong nuclear force, again, you've come across that before. I've mentioned it in one of the videos. It's all to do with the attraction between individual quarks. Normally, we see this happening very specifically in fusion. Remember in fusion, when we get two particles that come close enough together, eventually the strong nuclear force takes over. Now, interestingly about the strong nuclear force, as you remember, it's extremely attractive at close ranges, but actually slightly repulsive at further distances, which is a little bit of a mind-boggler, but please do go back and have a look at that. But the strong nuclear force is effectively what allows the nucleons to stay together. Okay? This strong nuclear force allows the nucleons to stay together against that strong electrostatic repulsion. So think about, again, I'll just remind you, inside a nucleus you've got lots of protons, all stuck together, obviously, with some neutrons. Now, that electrostatic repulsion has got to be absolutely astronomical at this distance. So there's got to be something holding these charges together. And here it is. Here's what's responsible, the strong nuclear force. So let's go back and have a look at beta decay now, because we need to draw interactions or Feynman diagrams for beta decay. So as before, something's changing about in beta decay. Now, obviously, you've got beta minus decay and beta positive decay. And we're going to look at one example, because in lessons, you're going to have a look at what the other example may be, have a think about what it might be. So in this example, we're going to take beta negative decay. So if you remember what beta negative decay is, it's where a neutron becomes a proton. So we're emitting a beta particle. Now, often I give the example of in beta decay, we get the carbon-14 becoming nitrogen. Yeah, happy with that. That's not a problem. Neutrons becoming a proton. Let's just remind you of that equation up here. So carbon-14, apologies, and 6. And that goes to nitrogen 714. So you can see here that the proton number has gone up. So as you can imagine, the total nucleon number has stayed the same. So we've increased our number of protons. Hence, a neutron has become a proton. And as we're aware, we should hopefully remember that what is released in this reaction is an electron or a beta particle, -1, 0, and then our anti-neutrino, electron neutrino, is released to balance lepton number. So that's our reaction that we're going to look at here, and we're going to cut out kind of this carbon-nitrogen idea entirely. We're just going to go from, based on the interaction of the neutron turning into a proton. So in the Feynman diagram, you can draw this a number of different ways, and I'm going to draw it probably 2 ways on this picture, just so you can see. So in this case, a neutron comes in and becomes a proton. But how does that happen? Well, as we well know, an electron is given off. We've said that up here. Our beta particle, otherwise known as an electron. So in this circumstance, what we're going to look for here is a beta particle being released. Now that beta particle being released has to be, this interaction, as we've already mentioned, is governed by the weak nuclear force, W bosons. Now, think about this. The neutron comes in and becomes positive. So it's got to lose some negativity, as we said, well, that explains why the electron is there, so that the proton can become more positive. It's got to lose negativity. If you lose some negativity, well, as a result, you become positive. That's just like in life as well. So in this case, we need to release a boson, or we need to utilize an exchange particle to make that happen. So what happens is we have our W boson. Guess what the charge is on that boson? Well, that is the particle that's effectively moving this charge away from the neutron to proton, so it is a negative boson, a negative W boson. Please note W is for weak nuclear force, so you just need to bear in mind that that's why it's called that. So we're getting that negative charge being taken away via this exchange particle. Remember, it's a virtual particle. We mentioned that term before, so you can't observe this happening. But this exchange happens and the electron comes off. But we've missed something here. We've missed our electron neutrino. And so we also need to have our electron neutrino coming off here. But unfortunately, electron neutrinos are a little bit of a strange thing to observe here. And you'll notice on purpose I've not put the arrow in yet, and I'm going to do it in a different color just to highlight that the importance of this. Antiparticles go backwards in time. Yes, I did just say that. Antiparticles go backwards in time. So the arrow should always be facing towards the exchange particle in this instance, whereas the normal particle, I say normal, but the electron, the non-antiparticle, is going to be coming off forward in time. Okay, because remember, this is our time axis here. Please bear in mind that sometimes these diagrams are rotated, and I will literally just do it now. So these rotations can happen, and you can see the diagram in this orientation where you have the time axis going up here or up here, it doesn't really matter. But yeah, just bear in mind that that is a thing, and you may see Feynman diagrams in that orientation. So that's a interaction there, but there's something more happening here that you need to be aware of, and that's what's happening with the neutron. Well, we already introduced in previous lessons that we now know what the quark structure is of each of these two individually. So what is the quark structure of a neutron? Well, it's up, down, down. And the quark structure of a proton is up, down, up. So what does that mean? Well, that effectively means that one of these down quarks has become an up quark. It has to. That's what has to have happened for a neutron to become a proton. So when we look at what's going on here, instead of writing neutron to proton, oftentimes we write it in terms of the quark change that's going on. So we're going from a down quark to an up quark. So this whole interaction here, neutron to proton, is now better defined as a down quark going to an up quark. Oftentimes we do see the neutron and the proton detailed here as well, but we're just showing the fact that the down quark and the up quark is the actual thing that's changing here. Now, please note, actually, this interaction is of the most importance because this still shows that we get a whole value of charge of 1e given off in this interaction. What's the charge on a down quark? Well, the charge on a down quark is -1/3. And the charge on an up quark is +2/3. So, what's the difference between those two? Well, if you were thinking about it as on a number line, you'd have to remember that, well, -1/3 going to +1/3, +2/3, apologies. You'd have to change this by 3/3. Okay? And so as a result, you'd have to lose 3/3 of negativity. You'd have to lose that 3/3 of negativity. So if you take away a minus number, it's like plussing it. And as a result, you get this charge here. So the difference here is -3/3. So in this case, or in this case exactly, 1e, which is our charge here. So that explains where that charge comes from exactly, because there's been a change from -1/3 to +2/3. We've lost 3/3 of negativity to get 2/3 of positivity. So it all comes together in this Feynman diagram. This is possibly one of the more complex ones that you need to be aware of, and we'll talk about some other versions in lesson.